Okay, welcome everyone to TAMIDS Tech Talk series. So today we have Vinit Sehgal here from the Texas A&M University. And Vinit is a Ph.D. student from the Water Management and Hydrological Science program. And I got to know Vinit in one of our BYOD, Bring Your Own Data workshops. And I believe back then when Vinit just got started, doing the large scale simulations, he had some problem to scale his data analysis code on HPRC systems. So I talked with Vinit and I worked with him through a couple of sessions, and he got to use HPRC systems efficiently afterwards. And he has been working on this subject for a long while, probably more than 2 years, I believe.
Yes.
And it's really good. I showed him how to get started. Then he just picks things up and start working on things himself. And today we'll be talking about large-scale geospatial analysis with R. And myself, I'm a Python person, and it will be a great opportunity for me to learn a bit more about R through this. And also, Vinit is working with several other students from his group. They're organizing a workshop on the same subject, and I think you should have already, everyone should have already got an email about the workshop. So the workshop will take place this Thursday, and I believe you need to register for that one. For this talk, everyone can get access to it. We will record it, and the video will be announced. The links will be posted on the TAMIDS website. But for the workshop, you need to register through HPRC Google Forms, and the links to the Zoom, for the Zoom meetings and presentations will be sent to you afterwards. But with all that said, I'd like to welcome Vinit to the virtual stadium and give us a talk about the large-scale geospatial analysis with R. Now it's all yours.
Thank you so much, Dr. Tao. It's been a pleasure. Thank you so much for hosting this. First things first, this workshop is all about helping to give a perspective on what all we can do in R in terms of geospatial analysis. So as the title suggests, we will talk about large-scale geospatial analysis with R. I'm Vinit Sehgal, and I'm a Ph.D. student at Texas A&M University in Water Management and Hydrological Sciences. I'm doing Ph.D. and this will be my 4th year. So without further ado, let's go forward. A little bit of background on me, because that will lead us to where what we'll be talking about today. So I did my undergrad in civil engineering, where my focus on research was flood forecasting using data-driven and machine learning methodologies. So a lot of geospatial data was being used there as well, where we had to tag a particular river or a particular gauging station and try to see the geospatial relationship between different stations and how one station can affect another station. My master's was in biological systems engineering, where I studied how we can use climate simulations to forecast drought for southeastern US. So we were using a lot of model data, we were using a lot of climate data, and integrating them to give a comprehensive drought forecast for the southeastern US. And with any kind of forecast, as you all know, more than the values, the location matters. If I say that in a particular region in Texas, there will be a precipitation of 100 centimeters, without having a pinpointing a location, that forecast has essentially no meaning. So a lot of geospatial aspect was there in that data as well. And then I started working at Texas A&M, where I'm studying how we can use satellite soil moisture data to estimate soil hydraulic properties. And I'm very fortunate to have my office in the historic Scotts building. If you all know the building with the very beautiful blue metal door. So it's right opposite to this huge tower. And this is where my office is. And so now I'm working on a global data set coming in from soil moisture active passive satellite that NASA launched in 2015. So this satellite gives us global near surface soil moisture, which is around for first 5 centimeters of the soil profile with a resolution of 36 kilometers, and we have a global revisit in 2 to 3 days. So one of the prime aspects of using this data is, other than understanding soil physics, soil moisture data can also help us understand or better predict or forecast floods and droughts in almost near real time. So with a global coverage, with around 2 to 3 days revisit, this satellite or this data, this kind of data, in fact, can help us understand these hydrological extremes much better and even forecast them with better accuracy. So this is the prime motivation as why we wanted to do a large-scale geospatial analysis. And I'm sure the people who are here in this seminar as well, a lot of you have some background in working with the large-scale geospatial data. When I say large-scale, either we are talking about a huge extent, either at a continental scale, regional scale, or in this case, a global scale extent, or we have very high resolution that leads to having extremely high number of pixels within the extent that you're working in. And that is why you have a lot of data coming in after a certain interval. So either of these factors or a combination of those can land you into the domain of large scale data. I will not call it a big data as such, because we do not have the kind of velocity, or in some cases, we do not have that kind of variety in the data that generally is there in the case of big data, but I would surely call this a large scale data. And we'll look into how we can use R for large scale geospatial analysis. So we will talk about 3 things today specifically. First, why we need R for geospatial analysis, what advantages it has in terms of other available softwares that we have out there. We'll look at how we can visualize, and through some of these examples, we'll see how we can visualize this data. And second, what are the tools and what are the available opportunities for us using this platform or the open source libraries that we have, and what kind of general operations we can do. And because there are a lot of things we can do using any tool or any platform, but our focus will be what kind of general opportunities we have using this data, like what kind of general analysis we can do, so that when you are out there doing your work or doing your research, you know that this kind of analysis can be done in R as well, and not just in GIS or in any other proprietary software. And second, we'll focus on the simplicity of these functions. So other than complicating things way too much, rather than saying you can add 10 different things into this and do a very complex analysis, we'll talk about how to start slow. We'll talk about how to start with a very simple example, and then we'll build on that to give, instead of making someone afraid of this data, we want to make them be familiarized with data. That's why we'll focus on simplicity of this operation in R. And this talk is interactive. I would like to keep it that way. That means that in any slide, if you have any question or if you want to interject, please feel free. I would love to have an interactive discussion right then and there, and then we can move forward. The slides will have a lot of code snippets, and I know it will be extremely boring if we do not stop and discuss and ask questions at that time, and it will be too much by the end. So let's stop at any place that you feel that you have any question, and let's discuss, and then we'll move forward. And again, this is not a hands-on tutorial, as Dr. Tao has specified. The hands-on tutorial or hands-on workshop will be there on Thursday from 12 o'clock to 5 o'clock. So why use R for geospatial analysis? So other than all other tools, all other softwares that we have, some of you might be very much familiar with Python. That is one of the popular ones. Some of you might be using ArcGIS or QGIS or any other proprietary software as well, or even MATLAB for some cases. The advantage of using R is that it is free. We have a lot of open source libraries, and these libraries are ever growing. Other than that, we have exceptional data visualization capabilities that we are all familiar with or may be familiar with, and we have a large user base. By large user base, I mean a lot of people are using these libraries in near real time, And if there's a bug or there's something that needs to be changed, the developer gets a feedback on that. And another good thing that most of these libraries that we have for R have been published in peer-reviewed journals, something like Journal of Statistical Software, a very high impact factor journal. So as you can see, I took this a snippet from the journal's webpage today, and out of all these 6 listed recent publications, out of 6 publications, 5 are from R. So that gives an additional scrutiny to the packages that we are using here. So it had been long called that R is for statisticians, from statisticians, but using that huge statistical framework for something at a large geospatial analysis, that makes this whole infrastructure so powerful. So it is well weighted, it is free, and it has a large user base, and that is what makes this whole thing very powerful. So in today's example, in today's whole discussion, we'll be using 4 data sets. So it's good that I introduced the data set early on. So first we'll be using global surface data, soil moisture data from NASA's SMAP satellite. We'll be using global aridity, which is akin to saying the global hydroclimate classification. And then we'll be using more this NDVI data, which is a vegetation index. And as a shapefile, we'll be using updated IPCC global regions. IPCC stands for International Panel for Climate Change. So we have some standardized global regions where some of these big global scale models use these standardized regions to run or subset the data. And we'll be using this very standard data as a way to showcase some of the operations that we'll be doing later on. So let's start. First with a raster. I'm assuming that most of you will be familiar with raster data. If you are not, if you have any questions, please ask away. So the simple way in which we can import the raster, as I mentioned, that we'll focus on the simplicity of these functions. You just need to use one function, which is raster, and you specify the path, and you have the raster imported in R. And to plot this, all you have to do is to use the function plot, and you plot that raster, and this is how your output will look like. And if you print the attributes of this is where the real geospatial part comes into play. So in this raster, which is SM, soil moisture, we see that we have the resolution, which is around 37 kilometers. We have the extent, which is the global extent that we see over here in the map as well. And we have the CRS. The CRS refers to Coordinate Reference System. So we have this CRS, extent, and resolution, and that essentially makes this 2D matrix in a way a real geospatial data, because now we have the latitudes, we have the latitude on y-axis, we have longitude on x-axis, and now each of these cells in this matrix that we are plotting over here is geolocated. Sorry. Right. So as we were talking about the coordinate reference system, so one of the basic operations that we do, the first things that we do with a geospatial data is the projections. So if you project a geospatial data in a different coordinate system, you know how the data will look so different. So to reproject that, we'll use a function called project raster. And all we have to do is, after this function project raster, is specify the raster and specify the coordinate system we want to project this raster to, and it will project the raster to that specific coordinate system. In R, the coordinate systems are given in ESPG format, which is a numerical format, something which is shown over here on the left-hand side. In this case, we have ESPG 4267. These are standardized coordinate references or standardized numberings for a specific coordinate system. For example, NAD 83 projection can also be written in the form of ESPG and this 4-digit number. For details on them, you can refer to their website, and every coordinate system can be referred in terms of the standardized ESPG format. If you do not want to use ESPG and you want to use the full format in Proj 4, you can do something like this. So it has the projection, it has the longitude, X, Y, and we have the datum and units, and all those go into this. And we specify the projection for our raster, and we project this. And this is how different, if you compare the plots on X and Y axis, both of these plots look strikingly different from each other, because now the projection system has changed. And we started with this projection system, which was a lat long and standardized format. And now we have gone to NAT83 or Robinson, and that is why the projection has changed. And that is why the rasters image are looking so different in each other.
Hey, Vinit, which one is the most popular one used in the community?
It can be either ESPG 4263, NAT83, or the most popular one is this one. As you can see, we have WGS84, and in the most standardized format, basically using a simple latitude and longitude, we have WGS84, which is given like this.
Okay, thank you.
So, although the data sets and the projections will change based on the source of the data that you are importing the data from, but the most popular one, as the question was asked, the most popular one is World Geographic System 84, where we have the standardized lat long format. And then we can project them into any specific format that you might want them to be. And after that, yes. So we have talked about how to just make simple plots, right? You remember we were doing simple plot function and we put the raster and it gave us this. Why not we add multiple options to these? Like we want to add the title to this, we have to say main and then the title. If we want to add more different options or want to use additional features, all we have to do is we have to give the plot title over here using main. We have to give the lab label breaks using this. We can give color breaks. We can specify the color. We can specify X and Y label, and whether we want to interpolate this map or not. And this will make the plot look like something on the bottom right. So we have gone from a very simple plot over here on top right to a plot with many more features. Like we have standardized the color bar, we have changed the color map, we have given the gray background, we have the X-axis label, we have the Y-axis label, and now the plots look much more better, or I would say the plots look much more publishable in this case. And we have had a question. Are you going to share the slides? I will share the slide. If you write an email to me, I would be happy to. Otherwise, I feel like the video will be available on TAMIDS website as well. And if you want the codes and if you want a hands-on feel on the codes, we'll be doing that on Thursday. And so we have started with simple plots. And now let's see how we can make them even prettier or even more publishable using some advanced functions. So if you see, I have given a source over here. Basically, this is a custom function which we made, which uses the imported raster file. You specify your specific color map that you want this map to be in. You specify the limits and breaks and give your name, and it will reproject the raster to Robinson projection system and add a global boundary lines, and it will give the lat long and degree formats over here. So this looks much more, this looks improvised compared to the previous plots that we had. So all you had to do essentially is to use this function, robin_ras, and add and specify your raster, specify these 3 or 4 options, and you'll have this beautiful plot. So this is a really good and easy way to visualize your data. And you can do the similar thing using ggplot2 library as well. And you see that we have all these options. I am sorry that it looks a little busy. I'll go patch by patch so that I can explain what each of these functions mean. So ggplot basically means you're initializing a plot. We'll be plotting this raster file as geom tile. So we have SM data frame. So we converted the soil moisture raster into a spatial pixel data frame. I'll explain that later, and we are using that for plotting. So essentially it has a longitude, latitude, and the values. And then you're specifying what color you want to put in. You have your color map over here, and you specify your labels, your breaks, and then x-axis label, y-axis label, and your plot looks entirely different from the one we have previously shown. So there are multiple ways of seeing the same data and visualizing the same data. So another thing that one might want to do is, if we have a global data, but you do not want to plot the data for the entire globe, you might want it just for a specific extent, or maybe in this case, as we have shown Australia, all you have to do is add this specific feature at the end of the code. What it will do, it will fix the coordinates of the plot to these X and Y limits that you mentioned over here. So basically they define the extent of the plot, and you can cut the plot to a specific extent. And in this case, by using the same data that we have for a global analysis, we can just focus on a particular region that you want to plot your map for. So that is a very easy way of cropping your visualization. Instead of cropping the data first or masking the data first and then plotting, you can just plot the map for a specific region by just using one single function.
Hey, Vinit. So for the plot here, for the color map, but the color map itself will be covering the whole map, not just the, go to the next one. Now you have a fixed, excuse me, have a fixed region, but the color map itself is going from the maximum minimum to the whole map, right? For the Australian one.
For the top plot or for the bottom plot?
For the second, the next slide.
For this slide? Slide 13? Okay.
So I'm talking about color map, like SM here is going from 0 to 0.8. But in the plot we are showing here, just it has a very small range. Are there any ways that we can just limit the color map to the right?
Yes, you can, because in that case you can limit. You see this option over here, limits. So in this case we have limited the color from 0, the values from 0 to 0.8. That is why this color map goes from 0 all the way to 0.8, because this is just an exact replica of the global data that we have. So you can see in some cases the values go really high. In northern latitudes, the values can go really high. So we use the same limit that we had for a global data set, but because we are plotting it for Australia, we can see that the values are not going that high as it will go in northern Canada or in Siberia. But you can change those limits over here. If you just want to plot it for 0 to 0.4, you can change it to 0 to 0.4 and change the breaks accordingly, change the labels accordingly, and it will get plotted in the limit that you want it to be.
Yeah, okay, thank you.
That was a great question. Thank you so much. And now, because we have already covered rasters quite briefly though, but we'll talk about them more with respect to other geospatial data as well. So other than rasters, we have shapefiles, which are very important for geospatial analysis. And just like rasters, working with geospatial files, with spatial data frames or spatial polygons is also very easy. So just like raster, where we had one line and one function to import raster, over here we have just one function to import this shapefile that you have on your disk. So we are using read OGR. You can use several other functions which are available. That, for example, we have SF, from SF library, we have string underscore read, st underscore read function, which does exactly the same thing. But in this case, we'll be importing this data, which is a shapefile, as OpenGIS simple features reference. So it is called OGR, I'm sorry. And we'll import this shapefile as IPCC underscore shape. And if we plot this, we see that we have different regions that we were previously talking about, which are standardized global regions based on the IPCC classification. So the whole idea is that we want to use this shapefile along with the raster file to explain different geospatial functions like cropping, extend, or masking, or export, or some other function that we'll talk about later. So for now, just like the raster was the geospatial data, the shapefile is also geospatial data. And that is why we'll see we have an extent of this particular file. We have the CRS, which is the coordinate reference system. And now we have 41 features. Each of these features is essentially one of these polygons. So this IPCC shapefile is a conglomeration of multiple features which makes this particular plot, but it has in total 41 smaller polygons. So if you print the header of this shapefile, you'll see we have the names, the continent, we have the name of this region, we have the abbreviation, and we have the numbers of each of these features. And if you want to plot or color these shapes or these polygons based on their color, you can just select plot, the name of the shapefile that you have imported, and then you can specify which particular row you want for color. In this case, we wanted color from V4 feature, which is the numeric feature that we have, and that is why we use that for coloring. And you can see that each of these have a different color. And next is how to use the polygons, the shapefile, along with the raster, because that will lead us to some of the more advanced functions that we'll see today. So again, to go through the IPCC shapefile structure again. So we have the shapefile where we have each of these polygons have its specific continent, its name, its abbreviation, and number. So what we want to do is we want to plot this on top of a raster file to see how it looks like. So just like we have seen before, I am plotting the raster using plot function over here with SM and specifying the color format that I need. And just after that, I'm using another plot function for the shapefile. And all I'm doing is the only difference that we have here compared to the previous code is I'm adding add equals true. So whatever shapefile we have after the raster, it will get superimposed on the raster, and it will look something like this in this case. And in case you want to subset a particular feature from this a global shapefile, you just want a feature for Eastern US or Central US or something. In your case, it might be entirely different, but just to show you an example as to how you will subset the features from the shapefile is by using this simple function. So IPCC underscore shape, and just like as you would subset any data frame or a matrix, you are just taking the fourth row and all the columns, and that takes out all the data for a specific spatial polygon in this bigger set of polygons. So in this case, I have extracted the spatial polygons for Western North America. If you see over here, it is this patch which covers US Northeast, and we have part of Florida, almost all Florida. And this is the polygon that I want to extract from this larger chunk of data. And all I have to do is I have to subset it as I would subset any matrix by taking all rows and taking a specific, by taking one specific row that I want to extract from this big data. So now this is how the polygon looks like if I plot just for Western North America. So this is a smaller subset of the big data that I have over here. Any questions?
This one looks like it should be Eastern, right? Not Western.
Yeah, this is, oh yeah, that's a good point. Sorry, this is Northwest North America. So NW North America, this is the fourth feature over here. Sorry, no.
This is the polygon.
Oh, no, that is a good question. Right, that is actually a very good question. So that brings us to this. So we are subsetting the fourth row and taking all columns. So that brings us, because this feature starts from 0, so we have 0, 1, 2, 3. So it will be Eastern North America. So we are taking this particular row, the fourth row, which corresponds to Eastern North America, and we are placing it over here. Thank you so much. That's a great observation. Thank you for pointing that out. So moving forward. So now we want to see how we can use some of these features that we have seen in a bigger polygon or shapefile to crop or mask our raster data. So we'll use a shapefile to crop and mask our raster data, the soil moisture data. So let us select the IPCC region first, just like we have shown. So we are subsetting the region for Central North America, which is the third row. And this is how the region looks like. So you can see that if I print the attributes of this region, this selected region, we see that it's a spatial polygon data frame. We have the extent, we have the coordinate reference system, And we have the 4 variables where we have the name and its abbreviation. So it is CNA, which is Central North America. So what I have to do, I want to crop my big global raster that we were showing over here just for this smaller region. So the functions that we'll be using, which are very similar to other geospatial tools which are available like GIS as well, we will use the function crop to crop the raster. So all we have to do is specify the function crop, put your raster over here that you want to crop your data from, and use extend region. So what this function will do, it will crop the raster to the extent of the spatial polygon that we have over here. If you do not want to use the spatial polygon, you can just specify your extent over here. But in this case, it is easier, and that is why we are using the extent of this region. So once it is out, your data will look something like this. So you'll notice that this part of the region is going out of the selected region. Why? Because the raster was cropped for the extent of this shapefile, that is xmin, ymin, xmax, ymax. So it will not remove this extra part over here. And to do that, the function that we will use, just like ArcMap or ArcGIS, will use the function called mask, which will mask out any of this extra data set which lies out of this region. So if we implement mask on the outcrop raster and we specify the region, it will give us this value. So now from a global data set, we had a subset of that data for just the extent of the Central North American polygon. And now we have the data within that polygon. So in case you're working on a smaller region and you have a data for a larger part or a larger region, and you do not want that extra load on your disk or when you're importing the data, you can crop, you can mask and save it somewhere else. And then that will make your work much more efficient and faster. And in case you do not have any shapefile and you want to take advantage of some of the data set that comes with the raster library in R, it has a package called it has a package called raster, which comes with some of these functions called get data, which can pull in these global administrative boundaries from GADM sources. So there's some open source resources available on web, and this function can pull the data set from that resource. And in that case, without having this file located anywhere on our disk, we can pull it right from the web by using the function get data. And we need GADM and we need the data for the country USA in this case. And you see that we are specifying level 1. That means we want the data at a state level. So from that, we are subsetting the data for just 3 states, Colorado, Texas, and New Mexico. And when we plot that, this is how the imported shapefile looks like. It is important to note that this shapefile was not imported from our disk, but was pulled by this function from web. And now we are using the same functions that we used previously to crop and mask the data, but this time we'll be cropping and masking the data for just the 3 states that we see over here. So we have a cropped output over here and we have the masked output. So from a global data that we have seen previously, we were first cropping and masking for a specific region using a shapefile on the disk. And the next, what we have seen is we are importing and cropping and masking the data using the data that we have pulled in through this function from the web. So it makes it very convenient. Even if you do not have a shapefile on disk, you do not need to download it separately. You can just take advantage of some of these functions, and you can do your analysis for a specific region. Any questions so far?
Yeah, Vinit, there is a question in the chat room.
Just a second. So Deepsha asked a question that instead of shapefile, can we import user-defined text file, longitude, latitude of boundary points and covalent raster? The answer is yes. If you have a text file or a CSV or in any format where you have latitude and longitude, essentially all you have, what you have is the extent of the data. So first thing that you have to do is convert that .text file or that CSV file into a spatial polygon, and there are functions for that. You can talk to me separately about that. Once you convert that into a spatial polygon, everything else remains the same. And essentially, there's just one single line of function which can convert some of these spatial data points into a spatial polygon. So all you need are the vertices of the region that you want, or the vertices of the polygon that you want. So if that is in a text file, that's okay as well. Does that answer your question? Thank you. That was a great question. So there is another way of doing this. So in many cases, you might not have a shapefile. If you have if you have the vertices of the polygon that you might be working with, you can import that. You can convert that into a polygon, and then you can do all this cropping and other and masking that we have shown over here. So let's go forward. Just excuse me. So now we'll be talking about another important function, which will be, which all of us, if we have worked in GIS, might have used, and that is called extract. So if I have a spatial point, and I want the values just for that particular point, and I don't want data for the entire globe, I don't want data for a region, I just want data for a specific point, the function that we will use is called extract. So what we do is, using this function, either we can extract point for the latitude or longitude. Otherwise, we can use extract function to summarize the value between each polygon. To explain what we are talking about is, just look at this figure on the bottom right. So we have data for 3 states, Texas, New Mexico, and Colorado. And if I need the mean values of all the cells within Colorado, or if I want the values for New Mexico or the mean value for Texas, I can use extract function to extract the cells within each spatial feature, and then use a particular function, be it mean or median or any other user-defined function, to summarize the values between each of these polygons. Let me highlight what I'm talking about here. So using this function extract, I'm using my raster to summarize the values. The values have to be summarized for the features in IPCC shapefile. You remember the global polygons that we were talking about here. So what we are doing is, we are summarizing the values for each of these spatial features. So now I need the data in a data frame format. The output should be in a data frame. That's why I say df equals true. And you see that I have used a function mean. In this case, I want the mean value of all the cells between each of these features. And if I run this code, I get the mean values of mass soil moisture for each of these features. And in many cases, you can use mean, you can use median, model, or any other function over here. And in case you have a specific custom function that you want to use, all you have to do is make your function, just like in this case, I have given a very small example by using the quantile function over here. So all this custom function does is it finds the 25th percentile of X, which should be an array or a vector. So I use this function, quant underscore func, instead of mean that I was using previously. And what this will do, by using this custom made function, it will find out the 25th percentile of the data within each spatial polygon, and the output will look like what we have on bottom right. So you can see that there's a difference in the values, because the value on the top right is the mean value for each polygon. The bottom right is the 25th percentile of each polygon, but the application remains as simple as it would be for a predetermined function or a standard function like mean, median, min, or max. And you can just change one line of code and you can do your custom analysis on each of these polygons. So it is as simple as that.
Vinit, there is a question in the chat room.
Just a second. How does extract handle overlapping polygons? So if we have overlapping polygons, I haven't used overlapping polygons as such, but if you, based on how the extract function works, it should be able to extract values for the overlapping polygons as well. The only difference will be for one polygon, it will take all the values between that in that polygon, and for the other one, it will take values under that polygon. So I think it should be okay to even for an overlapping polygon. So after this, as I briefly started talking about this, in many applications, you might need data for a specific latitude and longitude. And instead of the polygon feature that we used last time, what we can do is we can use the latitude and longitude of your interest, convert them into a spatial location using function spatial points. So now our knows, or the system knows, that this data that we specify in the latitude and longitude data, which is given over here, is a spatial data point. And using that spatial data point, you can extract the values from this raster. And in this case, I have used bilinear, which is an interpolation method, just in case you do not have the value lying exactly at the centroid of the raster pixel. You can use nearest neighbor interpolation also. In that case, you'll have to use the option simple. It will not do any interpolation by using the simple function. But if you use bilinear, it will do bilinear interpolation of the data set for the location. And in this case, the cell value, which if you can recognize, this is the lat long for College Station, and the soil moisture for the particular day for College Station was 0.18 meter cube by meter cube. And another way of finding the data for different X, Y, and Z, or in this case, lat long and the Z value, is by converting the raster to spatial points. So basically, we are converting raster into a spatial pixel data frame. What a spatial pixel data frame is, essentially, instead of raster, over here, where my computer knows that every single point over here has an X, Y, and a Z value, what I'm doing here is I'm just converting that into a longitude, latitude, and the value form. So now I have a data frame where each value has a longitude, where each cell has a longitude, has a latitude, and the soil moisture, or the corresponding value for the raster. So if you want to find the value corresponding to the specific location, in this case longitude and latitude, you can convert the raster into a spatial pixel data frame and then see which longitude and latitude is closest to your choice of location. And then the value on the rightmost column will be your value of interest. We have a question. Okay. So guys, if you have a question, feel free to interject. It will be easier if you can just stop, if you can unmute yourself and just ask the question away. But I'm really enjoying that how we are having really nice array of questions. That's really great. Thank you so much. So far, we have seen how to do all this spatial analysis for one single raster. Rarely our lives are so easy. So we have seen projection, cropping, masking, and summary statistics for just one raster. We are very fortunate if we just have one raster and we have to summarize and get away with it. But in many cases, we have data coming in for multiple days. We have data coming in from multiple sources, or we have data coming in for multiple variables in many cases. In that case, what we want to do is to repeat the same analysis that we have done in on one raster, but to make sure that everything is repeated on an array or on multiple rasters simultaneously. So that brings us to raster stacks. So essentially in raster stacks, we see we have, we can call them data cubes, because instead of one raster, we have X, Y, and Z values. So this is where the actual power of using R for geospatial analysis comes into action. So what a raster stack or a RasterBrick is, essentially for our practical purposes, raster stack or RasterBrick are a stack of multiple rasters. So we have longitude, we have latitude, and this can be time or a variable or something else. The only thing is the data set has to be exactly of the same extent if you want to stack them up on top of each other. So working with RasterBrick and raster stack, the functions, the codes will remain exactly the same. The only difference being the RasterBrick is stored in your local disk in your memory. So making RasterBrick takes a little longer, but because it is stored in your memory, working on RasterBrick is much more faster. But raster stack is basically making a virtual connection to different data sets. So making a raster stack is easy, But if you have multiple data points, if you want to work on a really large scale data, raster stack will be a little slower, but the functions, the application remain exactly the same. So let us see how we can make a raster stack. In this case, I have 23 files, which are listed something like this, just to give you an idea of what we're doing. Now, we are using NDVI dataset. We are stacking up NDVI data for multiple retrieval intervals, and they're converting that into a RasterBrick. So I have these files in my disk, and I want to create a RasterBrick out of it. So all I have to do is I'll use lapply on this list of raster files and use brick with that. So this will give me a RasterBrick of dimension. If you can see over here, we have the dimension 456 times 964, which is the X and Y dimension. And in that we have 23 layers of different rasters. So all the rasters which were there in this particular path, those have been converted into a RasterBrick. And because we had 23 rasters in this case, if you do not want to work on all 23, you want to subset them, all you have to do is just like you would subset a list. Notice these double brackets that you see over here. And I need the raster layers for 1, 1st, 3rd, 5th, 10th, and 12th retrieval. So all I had to do is I have to subset RasterBrick just like I would subset a list by saying, by putting double brackets over here and specifying the layers I want. And this subset RasterBrick will be a subset of just 5 layers, which I have specified over here. The question is, Dr. Khidun asked the question, is the function break in base R or does it need to be a package? As far as I remember, that is in raster library, so it should come with that. Once we have subset this, the prime reason why I wanted to subset the brick in this case is I wanted to show some of the plotting examples. So if you have the brick of 23 layers and you just write plot and the brick's name in the parenthesis, it will plot all 23 at the same time. So what we want to do is we want to make it simple for us to understand how this works, is just to show you how to plot specific layers in a RasterBrick. You can see that I have subset specific files over here from RasterBrick, and we have 1, 2, 3, 4, 5. And then if I plot it, it will make 5 plots. In this case, I think I have chosen the wrong image. And if you plot it using this function, it will give you another plot over here on the right-hand side. So it is just like you would plot a raster. The only difference will be instead of raster, you'll be using a brick and everything else remains the same. So that makes using a RasterBrick or raster stack so powerful yet so simple. This is just a fancier way to plot a raster layer. So instead of using a simple plotting like this, where you can have a lot of white space, if you do not want to do that, you can use another library, another function called level plot from RasterViz, and it will make it much more neater, much more cleaner. Just to give you a perspective, I won't dwell more on that, but just to show that some kind of advanced visualization that you can do using advanced and cleaner visualization that you can use with RasterBrick. And the next thing that we'll see is how we can use some of these summary statistics for RasterBricks or raster stacks. So what we'll see first is how we can find out layer-wise cell statistics. For example, if you're interested in finding the mean values of all individual layers, we can use a function called cell stats, which will apply a function on each of the layers and use the name of the brick and the function that you want to use. As simple as that. So cell stats will apply the function that you specify on each layer of the RasterBrick, and it will give you the mean value in this case for each raster layer. Similar example with quantile function. If you use quantile function and you use the brick's name for the probes 25 and 75, it will give the 25th and 75th percentile of each raster layer. So in many cases, you might have used quantile function or something similar to this for just a simple array or a matrix. The only difference we have over here is we are using a RasterBrick instead of an array or a list. And the same function is applied on all layers of the RasterBrick with such simplicity. And in case you do not want to use mean or mode or any standard function, you want your own custom function to be applied on each layer, you can make your own custom function like we have done over here. Use that in conjunction with cell stats with the same format. So cell stats, you have your brick and you have your custom function, and it will give 25th and 75th percentile in this case for each of the layers. And in case you do not want a local layer-wise statistics, you want a global statistics, one of the way of doing that is by converting the raster stack into a vector. That means the entire data in a raster stack or a RasterBrick will be converted into a vector, and you can use that to find any global statistics on the raster, like minimum or maximum. In this case, another function is min value. So it will give you min value for each layer, and you can use a minimum function or maximum function to find global minima and global maxima for the entire raster stack. Same thing for quantile as well. If you want global quantile, convert the RasterBrick into a vector, and you can find the first and 99th percentile for the entire data set, not just individual layer as you have done previously, but the entire raster stack. And another thing that I wanted to show over here is how simple it is to work on the entire data set. Say you want to normalize the values of each raster layer based on the global minima and global maxima that you have obtained over here. Over here, all you have to do is divide, just like you would normalize any vector, you would subtract the minimum value and divide that with the range of the data. So if you do that for RasterBrick, it will give you a normalized brick, and each layer will be normalized between 0 and 1. And in this case, I'm taking an example from one of the layers where it shows the normalized NDVI. So it is that simple and that powerful. You don't have to normalize each layer. You don't have to loop up. You don't have to write separate lines of codes. Just one line of code will implement all these functions on each layer and give you another brick with the layers of normalized data. And doing simple arithmetic operations, again, as I said, on RasterBrick or stacks are very easy. If you want 10, just as an example, on RasterBrick, all you have to do is RasterBrick plus 10. If you want to multiply each layer with 5, RasterBrick multiplies by 5. If you want to take, just multiply, have a data, subset it, multiply that with a specific number, you can do that as easily as I've shown over here. So arithmetic operations on raster stack and brick are very, very similar to what you would do with lists. So that is something that will really help keeping in mind. And if you want to filter your data, for an example, in this case, I wanted to filter out all the data where NDVI was less than 0.5. All I had to do was, this is the name of the brick that I'm using. RasterBrick is less than 0.5, assign that to NA. In just one line of code, I have flowed all the values where the values were less than 0.5 to NA. So it is that simple. As I said, that I'll be focusing on the simplicity of these functions. So that is what I wanted to highlight. So instead of going with every layer, doing this for each and every layer, you can just write one single line and it will operate the same function on each of these layers simultaneously. And the advantage and the real power of using RasterBricks over single raster layer, as I was mentioning, is that all the operations are done on all the layers simultaneously. Previously, we have seen how to extract the values for a particular longitude and latitude, and we came up with one number because we had one raster layer. Use the same function, extract, use the same operation of spatial points as you have previously done, and operate that on RasterBrick. And instead of single data point, you'll get a time series of data from all the rasters layer at the same time. So this is the power of using RasterBrick instead of looping it up over and over again. And this is an example on the right, on the left-hand side, we have the example of conversion to a spatial point. So previously we had X, Y, and Z. So now we have X, Y, and over here, you have the value of Z for each of the raster layers. So essentially, if you go from left to right, this is the time series of data for a particular long and latitude. Excuse me. That brings us to the topic of NetCDF files that we have. So NetCDFs are essentially structured data. And opening and working on NetCDF file in R is, especially in conjunction with rasters or bricks, is very, very easy. So to open raster, to open NetCDF files, we'll use a library NetCDF4. And in this case, we are taking this NetCDF file as an example. This is from SMOS IC, which is a European satellite for soil moisture measurement. And we have an NC file, which looks something like this. I'll explain that in a minute. So what we are doing is we have the NC file as a file name, and I'm trying to open the file using NC_open. And if I print NC, which is over here, print parenthesis NC, it will print the structure of the NC file, because the NetCDFs or H5 hierarchical data format, these files are all structured. So all of the variables have a particular structure, they're organized, and you can see the structure of the data over here by printing the structure of NetCDF. So you can see which variable is named in what format. Say, if you scroll down, this was a huge file, around 40 variables. I've just given some of the screenshots over here. So you see that the variable soil moisture is there with longitude and latitude. The fill value is this, the long name is this, the units are this. So if you scroll down, you'll see the structure, you'll see where each of these variables are located. So if I want to extract a particular soil moisture variable, so say in this case, we have the variable soil moisture as given over here, soil_moisture. So I have to use the function NC_var_get. So I need soil moisture variable from the NC file. So that's what I'm doing here. I'm extracting latitude, longitude, and also the flag. And remember to close NC file in case you have many, many NC files, because every time you close an NC file, the connection is stored in your local disk. So if you have multiple files, it will eat up the memory of your system, your R system. So now I'm closing this NC file. So I have extracted soil moisture. If you see on the bottom left, soil moisture, latitude, longitude, and the flag. So now I have these 2D matrices for each of these variables. So I'm deleting the values where the data is flagged. So where the data is not flagged, I'm keeping just that data. And any value where soil moisture is less than 0. In this case, it is just to show how you can filter or subset the data. So after you extract the values from the NetCDF file, it will be a 2-dimensional matrix. So you can do all the matrix manipulation that you can do on any other matrix as well. But the difference that we have over here that I want to emphasize is you can convert this data 2D matrix into a raster using the function map2ras. So now we have converted the soil moisture data using the longitude and latitude given with the NC file. And now we have a data which looks something like this. So these lines that you see, these are the swaths where the satellite was passing over on a particular day. And this was an example on just one NC file or just one H5 file, HDF5. It is worth noting that the same function that we have used for NC file can be used for HDF5 files as well with an extension .h5 or grib. It works with all those formats. So this is a very powerful library. And if you have multiple NetCDF files, in many cases, people are working with the model data where you have multiple outputs. All you have to do is loop up the code for multiple input variables, initialize an empty brick in the beginning of the loop, and store or add the raster that you have created in that empty brick in each layer by using the function add layer. So at the end of the iteration, you will have a raster stack for all of the iterations, and you can do all the geospatial data analysis that we have shown in the presentation so far by using this newly extracted RasterBrick. And some notes on HPRC implementation. It's just an example of something that I use in my research, and Dr. Tao helped me a lot with this implementation, because I wanted to simplify some of the analysis that I was doing by, this is a very layman's parallelization. I had a global data, as you can see, and to make it faster to be implemented and to get the analysis done, what we do is we crop and export the data for each sub-region in the world. And for each of these regions, we run a separate script. So it is that many times faster. Each job is smaller, but at the same time, all of them are being computed at the same time. So that is just to think about something. And so just to conclude, we have several options which are available in R for this geospatial data visualization. And this, as we have seen, is a very powerful infrastructure for statistical analysis. But when we group that with the geospatial application, it becomes really, really powerful, especially if you are looking to go away from a manual system like ArcGIS or something else. And the material discussed over here is not at all exhaustive. There's a lot and lot more material available out there online. So explore. I would encourage all of you to go explore and be creative and look for newer ways and newer things to do things. And if you have any questions, if you want to chat more about this, if you want presentation of the code, email me at vinit@tamu.edu. And again, special thanks to Texas A&M Institute of Data Sciences and Dr. Tao for facilitating this. Thank you so much. And feel free to ask any questions if you have. Thank you.
It's great. Any questions?
There's one question on working with buffers. Yes, you can work with buffers as well. Most commonly, we have buffers based on spatial distance, like a few kilometers or a few meters. And the function, I believe, is buffers. You can look up how to use buffers on rasters. We generally have circular buffer. I'm not aware if we have a square buffer around a point. I hope that answers your question.
Okay, so we have time for probably one more question. Okay, I think you should have access to. You should be able to get us to the slides as well as the other materials on the TAMIDS website, and the video will be uploaded there. And you should have Vinit email address as well. So if you have any questions, feel free to just email him. And if you have any questions or comments about the tech series, or you want to present your work, and I'll be more than happy to host you here at TAMIDS. So with all that said, thank you so much, Vinit.
Thank you so much, guys. Thank you so much for coming. If you have any questions, feel free to ask or email me. I'll be more than happy to help you or discuss more on this. Thank you so much. Bye.
Great. Talk to you later then. Bye-bye.
Thank you.